Ohio. Okay. I suppose Hawaii would also work. All right, we got about a minute to go. Oh yeah, Hawaii. Yep, I'm drinking coffee a little bit late in the day, but since tomorrow is Friday, it's okay. Yep, I'm drinking. I have been drinking black coffee for some years now, so there's no sugar, no cream in it. It's just black coffee. But we all know that coffee is it's kind of like a loan of time. So we are borrowing time from our own future. There's no way to create more time. You can only reallocate time a little bit. Green tea sounds good. That sounds a little healthier compared to coffee. But I need something strong. I can drink coffee and sleep like almost right away. Yep. Kind of insensitive to caffeine now. Cool. All right, so it is time to get started. So the first thing we'll do, the first thing I'm going to do is I'm readjusting my IEM because I think the ear tip is near its end of life. So, it's probably about time for me to change it. You can delete your time. I guess if you're a Time Lord, you can probably do that. Yep. But I'm not going to tell you guys more Doctor Who jokes because those are good, but it takes a little bit of effort to do it. All right, so what we'll do is we are going to finish the code for the assignment that we do today, and I am not even going to spend time to go back to the notes. So we'll just go ahead and write pn dash and make that greater than 0. So as long as the exponent of 10 is greater than 0, we'll do the following. So this time what we need to do is to decrease the exponent of 10 by 1 for each iteration. In order to decrease the exponent of 10, we need to multiply the mantissa by 10. So in principle, this is what we want to do. Okay, we basically want to say for each iteration, exp10 is going to decrement by 1. And in order to compensate for that, we also want the mantissa to be multiplied by 10. Okay, so this will work for the most part already, but it will only work for certain things. Okay, I have a phone call that I cannot answer, but I'm gonna have to text back because this one is kind of important. So let me just text back first. Okay. Okay. Sorry about that. Here we go. Yeah, my mom, who lives in San Francisco, bumped her head, and she has a 5 centimeter wound on her head. And they are thinking about my dad and my sister who came up from San Diego, and she is an ER doctor, so we do have a doctor with her at this point. So before this, we were talking about sending her to ER and getting an appointment with at least a Kaiser doctor to talk to. So my sister is probably just calling back to letting me know what the condition is. It's not going to be too serious, okay? Yeah, because the whole thing happened more than 12 hours ago. It's just that, she promised that she would call back and let me know how the situation is. So that's just kind of what the situation is right now. Oh, thank you, Tom. Yeah, I hope she would, get well soon. The issue is, how to make sure it doesn't happen again. So that's the thing. All right. So getting back to this program here. So the key is what number should we use to test this, right? Because if I don't give you an exponent of 10 that is high enough, it is I'll give you an example of what I mean by that. Okay, so if let's just say that the example is 1.23 times 10 to the power of 10. Okay, that value is well within what a 64-bit integer can contain, and as a result, the loop as it is now is going to work. Now, on the other hand, if I change the exponent of 10 to 50, then we know that at some point this is going to overflow, because we know that as an unsigned 64-bit integer, the largest value we can store is about 1.8 times 10 to the power of 19, and this one is way over that. So now we just have to be sure and say, well, when we get to this line here, that says Mantissa equals to Mantissa times 10, we better make sure that multiplication by 10 to the Mantissa is not going to exceed what a 64-bit number can store. So that basically means, if Pn points to Mantissa is greater than or equal to U int 64 underscore max, I think divided by 10. Okay, so we can just do a division by 10 over here. So if this is the condition, if this condition is true, then we need to do something in this loop here. Because if the Mantissa is greater than or equal to U in 64 underscore max, which is 1.8 times 10 to the power of 19 or so, divided by 10, that means by the time I get to line 56, it's going to overflow the Mantissa. So the idea here is to use division by 2 in order to quote unquote make room for the multiplication by 10. So that means over here, we'll say Mantissa is going to be Mantissa plus 1, and then the whole thing divided by 2. The plus 1 is necessary because it's a rounding mechanism. So if we don't do a plus 1 first, and then we just divide it by 2, then we end up with a biased error again. So this one is necessary. And then the next line is going to, now, because we changed the magnitude of the Mantissa. Yeah, it's my kitty. Where is he? Oh, he walked somewhere else. This sound means that my kitty is carrying its baby, which is a stuffed animal that looks like a cat, walking around, announcing to everybody and say, "Hey, look at my baby! My baby is here!" Yeah, he's both cats would do that. They're brothers, and they share one baby. Yeah, that's a kind of awkward situation. Okay, so for subtraction, it will always be plus 5. Not quite sure what that means. Yes, so the rounding is only needed when we perform division, because multiplication by 10 does not introduce an error, but division by 2 does. All right, okay, so because we are decreasing or we are halving the Mantissa, so that means we have to make it up by incrementing the exp2 or the exponent of 2. So that's just an increment right here, okay? So these two lines together, line 53 and line 54. Okay, Daniel says it's always plus 1 and then division by 2. And of course, those are in parentheses, so that is correct. Right. That's the whole point of rounding, because rounding means whatever you want to divide, we will add half of that to the numerator or the dividend, before we actually perform the division. Now, fortunately, we are converting to base 10, and 10 is a multiple of 2, so it just works out really well in this case. All right, so I think this code will do it, and somebody's going to say, but Jack, you forgot about this thing here. Okay, this code is actually still needed, okay, because this code is, and then end1 says, is line 51 greater than or equal to or less than or equal to? Let me check. It is indeed greater than or equal to, because we're basically saying if the mantissa is too large already and there's no room for a multiplication by 10, then we will make it smaller by halving it. Now, sometimes it only takes 3 iterations through the inner loop, and other times it will take 4 iterations in the inner loop. That's because 10 is between 8 and 16. So occasionally it is just 3 times, because 2 to the power of 3 is already 8. And other times it's going to be 16, which takes 4 iterations to cut it down to a value where we can multiply by 10 again. All right, so let's give it a spin. Okay, so let's give this a spin by clicking on debug, and then we'll run it with a dash n. We'll try that to 1.23 times 10 to the power of 50. Okay, and of course I forgot to set a breakpoint first, so we can go ahead and set a breakpoint right there. Okay, and then we just say enter, and now we got to the breakpoint. Yep, thank you, Daniel. And then we say print star pn. So now we need to check a few things. First of all, we'll have to check whether the mantissa has the most significant bit being a 1 or not. Okay, so I would give you guys another way to do this. Okay, last time we introduced 2 ways to do it. One is to print it as a base 2 number and then just count and see if the most significant bit is a 1 or not. Super tedious. The other way is to print it as a hexadecimal number, and then we have to check whether there are 16 digits or not. If there are indeed 16 digits, then we check the most significant digit to make sure that that is at least 8. So today, I'm going to give you yet another way to do this. Yeah, there are so many ways to do the same thing. So this time we start with mantissa, and this time I use a right shift operation, which is the exact opposite of the left shift operation. So this operation is moving, yes, literally moving all the bits to the right-hand side, and it will introduce zeros from the left. Okay, so every time we shift every bit to the right-hand side by 1 position, a 0 is shifted into the number from the left-hand side. Okay, so Anita is typing something. I'm going to wait a little bit as I sip my coffee. And Dan is typing something. Oh, okay. Yeah, the outcome was kind of intended for that purpose, so that you guys have some idea of how how we manipulate all the different properties or members of the number. And then Dan is typing something. I'm gonna wait a little bit too. All right. So, is it possible to cast the binary representation to a string and then just print the size? Yes, you can do that, but we do not have a variable that is a string that is easily accessible to the program at this point. So it's not a viable solution, just because we're in the debugger and right now we don't have access to a string. But we can do this. Trust me, this is even better, okay? Because we basically do a right shift by 63 bits. So what a right shift is doing is bit 1 becomes bit 0, bit 2 becomes bit 1, bit 2 becomes bit 1, bit 3 becomes bit 2, and so on. That's right shifting by 1 position, right? So if you right shift by 63 positions, that means everything is shifted out of the number except the original most significant bit. That bit, which was known as bit 63, will now become bit 0 after right shift by 63 times, and we just press the enter key, and it is a 1. That is telling us that bit 63 is indeed a 1. Okay, So this is yet another way to do it, and I can think of another way to do this, which is slightly less concise, but it will get the job done too. Yeah, so bitwise operations are very useful. Okay, your bitwise AND, bitwise OR, left shift, right shift, those are all very useful operations, especially if you write driver code, because most of the chipsets, to control your sound, the USB controller, the SATA controller and whatnot, most of the controllers, make use of input-output registers, and input-output registers are bit field. They contain bit fields. In other words, this bit and this bit and this bit together is serving one purpose. That bit is serving yet another purpose, and so on. So you need to access individual bits, and control the content of those individual bits. But the bus is still a 32-bit, 16, or 8-bit bus. So that means whenever you read, you're reading 8 bits. Whenever you write, you're also writing 8 bits. So to isolate the change to only 1 or 2 out of the 8 bits, these operations, bitwise AND, bitwise OR, and all the shifting operations, they come in very, very handy for that sort of work. All right, so we know this is meeting one criteria, and now we want to check and see if the value being represented is actually correct. So this time I am going to cheat in the sense that I am going to use double, because there's no way I can actually do this without using double, or I can use a spreadsheet. I think it's better to use a spreadsheet. So here's my spreadsheet, and we'll just go ahead and specify the Mantissa, EXP10, EXP2, and then we just have to copy the components into there. All right, so this is the Mantissa, and we'll paste it over here. Uh-oh, that didn't work. Let's try it one more time. Uh-oh. There we go. Come on, let me select it. There we go. Right click, copy, and paste. Okay. All right, so that's 1, and then EXP2 is 103. EXP10 is 0, okay, which is good. So now we want to see whether the value being represented is preserved. So the value being preserved is the Mantissa, which is this value, times, well, I'm not going to bother with 10 to the power of something, because we know the power of 10 is 0 already. So we'll only do 2 to the power of basically 103, and then press the enter key, and we are getting back 1.23 times 10 to the power of 50. So that basically concludes the program, and also how to check whether the program is working or not. Okay. Are there any questions concerning the lab that was due tonight? Okay, I'm not seeing any questions. All right, so if there are no questions about the program that is due tonight, I am going to start with a lab. Tonight there's a lab that is due next Tuesday, and this lab is a little bit ahead of time in the sense that we haven't really talked about the processor architecture. But this lab is not really asking you about the processor itself per se. It's basically letting you to play with the tool chain that you need to use in order to work with the processor that we'll be starting to work with next week. Okay, I think today is going to be the last lecture before we actually start to play with the processor. But I want you guys to kind of get familiarized with the tool chain first. So the lab contains all the instructions already, but I will go ahead and go through the process just so that you guys can get a first-hand demonstration of what to do. So this is a folder. This is from the subfolder of processor, which is inside the folder that I have shared with you. So if you want to go to the share folder, you can go to the class Canvas website, go all the way to the top, and then go to shared folder. And then within share folder, there's one that is called processor, and that is what this is looking at. Okay, this is the processor subfolder of the shared folder. So you have access to this already. You have read access to this, okay? So whenever you want to save something or make a copy, you have to specify your own Google Drive and not to take the default. So the first thing you need to do is to download 3 specific files. One is alu.circ, the next one is regbank.circ, and the last one is processor0003.circ. So you can do a control click to select multiple files and then do one download. Or if you want to just download them individually, that works too. You just click on one, download, click on the other one, download, click on the third one, and then download. So how you want to do this is entirely up to you. So download all 3. Okay, so we'll say download, like so. And Google would zip the file first. You're looking at those online here, and it's also contained in the instruction of today's lab. So, it's okay. I mean, you don't even need to be following what I'm doing closely at this point, because, the instructions of the lab actually tells you what you need to do. All right, so I'm just waiting for Google to get 3 pretty small files, zipped, and it's taking a lot of time to do it. I guess I really should not be drinking my coffee because, that makes time pass even slower than usual. What used to feel like 20 seconds now feels like an hour. That's what overclocking does. Oh, seriously, this is way, way, way too long. Come on. All right. So I'm going to change my approach. Just go ahead and download each one individually. So we'll go. Where is download? Come on, download. Get link, move to. There we go. Okay, so we'll just download one at a time, and it's okay to leave, so quote unquote leave page. And we'll put it to save it to a location. So this is something that you might want to do, is to change the behavior of your browser. So it gives you a choice of what you want to do with the file, and not to open it automatically or automatically save it to the downloads folder, because you really want to know where your files are located. And I'll explain why that is the case. So click OK, and I'll just put it inside the the temp folder here. You might want to find a more permanent home to download it. Okay, now the zip file is done. Great. Okay, we'll save that too. Okay, we'll cancel the other one and then save this one. There we go. All right, so we'll save this one to the temp folder, and I'm going to change the name to something else. So we'll just change it to processor.zip in the temp folder. And once again, when you download, you probably want to put it into a folder that you know where it is, and probably not inside the downloads folder, because that's where you lose stuff, because you probably have a lot of files in the downloads folder already. All right, so that is done. And then what I'll do is I am going to zoom in, in my command line interface, and then go to the temp folder and then unzip that file. So unzip processor.zip. Obviously, when you're doing this in Windows, okay, you don't have to use a command line to do it, okay, because that's basically what Windows does. Because if you double click on the zip file, it will let you unzip the file. You just have to tell where you want to unzip it to. Now the next step is kind of you can do it without using the command line, but I would suggest that you start to get used to using the command line to do this, okay? So it is to run the logic sim using on the command line. We talked about this a long while ago. At the very beginning of this class, I think it's in the first week, I already showed you guys how to use the command line to start up logic sim, okay? But there's another reason why we want to learn how to do it on the command line, It is not obvious from this homework assignment, but in future homework assignments, it'll be pretty clear. So the one thing that we want to do, oh, funny. I suppose we can do that. I can, put it onto the chat, channel. So anyway, right now we go to where I have put this, the Logisim jar file. Okay, so I saved mine into this folder, and the name is logisim310.jar. Okay, so where you put that file is up to you. Okay, so this is how I just start a file, and I can now supply your processor 0003.circ as the entry point. Now the other two files are also needed in order for the processor to work, but they are requested by processor 0003. So that's why when you start Logisim on the command line, all you need to do is to specify processor 0003.circ. Then you press the enter key, Logisim starts up, and there we have it. This is the processor. Okay, so the processor does contain a few components that we haven't really talked about. So part of what tonight's lecture is going to do is to talk about those components. Okay, so I'll briefly explain the various components inside the processor. The first thing is to zoom out a little bit so that you guys get a more complete picture of what it looks like. So this is the okay. Let me change to the selection tool. This is the register bank. Okay, the register bank contains 4 registers, and you don't even need to zoom in to the register bank to see the content of the 4 registers. Register A has a content of all zeros. Register B has a content of all zeros. Register C is all 0. Register D is all 0 as well. Okay, so you don't even need to zoom in to the register bank to understand what the values are for these 4 named registers. So they're named A, B, C, and D. On this side, we have RAM, okay, which stands for random access memory. So random access memory is writable and is also readable. We use it to store the program as well as the stack and also global variables. So all of those things goes into RAM. And then down here we have ROM. Okay, this is read-only memory. So the ROM is not, the content of ROM is not supposed to change, and don't change it either. Okay, because the content that is already in the ROM is very crucial to the execution of instructions. So you don't want to make any changes to that content. So you will need to understand how to kind of access the content of RAM and ROM. So to access the content of RAM, you just kind of right click on it, and then you go to edit content, and that's going to pop up another window that looks kind of like this. So when you look at a window like this, you will see that the leftmost column are in italic because those are the addresses of the first byte of each row. So this 00 is referring to the address of the 00 that is highlighted. This 10, which is in hexadecimal, is the address of this 00 over here. This B0 is the address in hexadecimal of this 00 down here. So if I ask, point to location 9D, okay, where's location 9D? Well, this entire row is 90 because we can see that 90 is the address of this byte over here. So 9D is really just counting. Okay, so this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we borrow characters from the alphabet. So this is A, B, C, D. So the byte that I'm highlighting is at location 9D of RAM, okay, because we are looking at the content of RAM, which is this component over here. So do we have any questions about the content versus the address of memory? Okay, this is similar to how Minecraft sorts their files. Okay, but do we have any questions? Does everybody understand what is an address versus the content at an address? All right. So assuming that is good, okay, we can now close this window. And we can do the same thing with ROM. Right click on it and then go to edit content. But once again, be careful not to change anything, because if you change anything in ROM, I have to resize it outside of the captured area and then put it back in here. There we go. So one thing you notice is, hey, how come these each location has so many digits? Well, that's because each location in ROM actually has 26 bits instead of 8 bits. So that's why you see a lot more digits, but the organization is still the same. So if I were to ask you, go to location D70, okay, you look at this and go like, nothing is, there's no D70 here. Well, it's okay, you can scroll. So you basically just scroll until you get to D70. So we have D70 here, and this is the content at location D70. This is corresponding to location D71, and so on. So each row in ROM actually has 16 locations, and you can also see, I think that's the same in RAM as well. Okay, each row has 16 locations. So do we have any questions about examining the content of RAM and also examining the content of ROM? Okay, Aiden is typing. All right. So each address points to unique 4 bytes. It's not exactly 4 bytes. If you look at the number of digits, I think there are only 7 digits because there are 26 bits. But since we need, because each hexadecimal digit is corresponding to 4 bits, so that's why we need 7 digits in hexadecimal to represent the content of each location. Yeah, sort of 3.5 bytes, but in hexadecimal, it's going to use up 7 digits. Okay, Christy is typing something. Just to be clear, which one are we using right now? This is corresponding to ROM. This is corresponding to ROM because the ROM has a lot more locations. RAM only has 00 all the way up to F0 when you look at the leftmost column. The ROM has a lot more locations. And so does that answer the question? Okay, cool. All right. So because part of the lab tonight will ask you to access RAM and access ROM to find out what is the content at certain locations. So I need to demonstrate how to get to the content of a location, and also how to distinguish the address versus the content at an address. So do we have any questions about that discussion? Because if not, then I can move on and talk about the assembly. Okay. Looks like we don't have any questions. Oh, Aiden is typing something, so I'm gonna wait. All right. Can I just look back into RAM? Yes. So right click on the RAM and then go to edit content, like so. Uh-huh. So RAM was top right. That is correct. This is RAM, and this one is ROM. It's behind my face. That is interesting. Okay, I see. Okay, so let's move these along a little bit. There we go. It'd be funny for me to put a picture of actually a RAM and have the actual RAM behind a picture of a ram, the animal. That would be kind of funny. All right. So, well, then what would you do for Rom? I suppose a Romulan would do. No, 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 no. Romance, there's no romance in my vocabulary. Romulans. All right. So are we good so far? So when you need to answer the question and you want to know which one is RAM and which one is ROM, the quickest way and the easiest way to do it is to click on something and then look at the selection because it will tell you what it is. This is RAM and this is ROM. So that's also another way to distinguish what you're looking at. Cool. Okay, how come RAM has 8 data bits but ROM has no? The ROM has more than 12 data bits. It has 12 address bits. So there's the address and there's the data. Address bits correspond to it. Basically, it will determine how many locations are available, and then data bit is basically saying each location has how many bits. So they are completely different. They are different because RAM in this case is just conforming to the usual standard of we need 8 bits per byte and everything is counting in number of bytes. But the ROM, on the other hand, has a completely different purpose, and it'll be clear why the content of ROM has so many bits. Why it is so wide. ROM is not dynamic in the sense that the content cannot change on the fly while the program is running. It is dynamic in the sense that you can control which location is the output. But we'll get to the discussion of RAM and ROM later on. Right now, I just need you guys to know which one is which one and how do we get to the content of RAM and ROM. And Christy is asking how do we distinguish the two. So when you look at the ports of RAM and ROM, you would notice that RAM has a lot more, okay, because it's read and writable. So that means we have one pin or one port called LD to basically specify are we reading this time or are we writing this time. And also because its content is overwritable, we also have a special port called clear so that we can zero the content of RAM. Okay. Let's see. It also has a pin here. Okay, you cannot see it right now. Let me magnify. Then you can see the little triangle. Okay, move a little bit right there. So you see this little kind of wedge or triangle here? That is the clock pin. It is unique only to the RAM because ROM doesn't need it. So from the appearance, you can actually kind of tell which one is which one already. But if you click on it, you will know for sure which one you're looking at. Okay. So those are all very good questions. All right, cool. So these are all very good questions. But for the assignment purpose, we don't need to get into the mechanics. We don't need to understand exactly how they are used. We just need to know what they are and how we can look at the content. Aiden says, I don't think I have the patience to make a Vim in Logisim. There's not enough space to make a Vim in Logisim because we only got 256 locations. There's enough to write Fibonacci in recursively, but not enough to do much more than that. But we'll get to that point. Okay, things will get kind of exciting as we go. All right. So, okay, so now we have to look at another file, okay? Another file that we need. Oh, VM, virtual memory. Okay, I thought you mistyped Vim, VIM, which is the editor, because that takes a lot more bytes to specify compared to relative to what we have. Virtual machine, yes. Well, this is a virtual machine. I mean, if I go back to here, this is a virtual machine. It can actually execute code. So now the question is, what does code look like for this particular processor. So that's a huge long discussion that we'll be doing for the next 2 or 3 weeks. Okay. So what I'll do instead is I'll just show you the tool that will crank out the code that you can put into RAM, and then we can run the program. Okay. So we are going to go back to the shared folder first. So we go back to the shared folder, which is right here. Okay. And there's an assembler. Okay, so double click. Okay, you don't want to just double. Okay, go ahead and double click it. You can still open it. But after you open it, you can't change it because this is my shared folder. So to you, it is read only. So to do the homework assignment, the first thing you need to do, if you want to use the assembler, is go to File, and then you go to Make a Copy. Now you have to be very careful, because if you just say, I'm just going to take the default and click OK, then nothing is going to happen. Because by default, it is making a copy in the same folder, which is read only to you. So it's not going to work. So what you need to do is to click on Folder and navigate all the way back to your Google Drive. So you're going to have to click, the back button until you see, My Drive. And then once you get back to My Drive, you won't see the folder that I have. You will be seeing your own folders. At that point, you can create a new folder if you want to, or if you have a place to put it already, then you can navigate to the folder where you want to put a copy of the assembler, and then click Select after that. So don't forget to navigate around when you're making a copy of the assembler. And after you make a copy, then you want to close the one that is in the shared drive, and then open the one in your own drive, on your own drive, because you're going to have to change the content of one of the sheets of this particular spreadsheet. So that's why you want to only use the copy that you have created. All right, so there are many tabs to the assembler, and we start with the source tab. So the source tab is where you insert the source code. You can copy and paste, but whatever you do, only do it to column A. And when you copy and paste into column A, do not copy and paste when you see the blinky cursor like this, because this way you can actually put in multiple lines in the cell, which is not how the assembler works. The assembler requires one line per cell. So this is where you have some flexibility in terms of how you want to do things. For those of you who like to use your own editor, you can just go ahead and use your own editor. So let me just illustrate what I mean by that. So I'm going to go to Accessories, and then go to Mousepad, which is equivalent to Notepad. Notepad is going to be fine, okay, for homework assignment purposes. And for the first one, you don't even need a mousepad or Notepad, because the code is already provided in the lab. So you can really just kind of copy and paste if you want to. Okay, so I'm just going to specify a fairly dumb program corresponding to a bunch of no ops and a halt instruction. Don't worry if you don't know what is a no op instruction versus a halt instruction. I'm just setting a very I'm just illustrating how to use it. Okay, so the actual instructions are not important. Okay, it is just the tool and how to use the tool that is important at this point. So once you're done editing your program, you can now Control A, select the whole program, Control C to copy to the clipboard, and then switch over to here and then paste it. So let me illustrate what is wrong first. Okay, double click it, see this blinky cursor in the cell, and then you paste. This is not how we want to do it. Okay, if you do it this way, it won't do the job correctly. So let's go ahead and so it's going to complain, because it doesn't understand that this is actually these are 4 instructions. It will look at this as one single instruction. So let's go ahead and erase this. So when you paste, you want to paste when the cell is selected in column A, but it doesn't have a blinky cursor in it. Okay, so you now Control V, paste it, and you can see how each line has its own cell, that means it is correct. Now, if you do something, and paste something that is not an instruction, incorrectly, so we'll say blah, okay? Then the assembler will do what it is supposed to and tell you that, hey, I don't know this, okay? It does have some elementary, error checking, or as much as I can put into a spreadsheet. So, so now we can just go ahead and delete this cell over here. Whatever you do, don't touch column B, okay? Column B has some actual code in it, and if you touch it, okay, then bad things will happen because you're going to break the spreadsheet. Now, if you do break the spreadsheet, which is bound to happen a few times, okay, no need to panic. All you have to do is to go back to where you got it in the first place, and then just reshare it, okay? Just get a copy, and delete the other one because you don't want to confuse yourself. Delete the other one, and then just make another copy. It'll be fine, okay? So if you do occasionally mess up the assembler, it's okay. Just make another copy and you'll be fine. All right, so this program doesn't do a single thing because all it does is to do nothing, do nothing, do nothing, and then stop. That's basically what the program is going to do. But the spreadsheet cannot run the program. Now, I suppose I could write a virtual machine emulator, inside Google Sheet using JavaScript, but I haven't done it, okay? And it kind of defeats the whole purpose of using LogicSim. So I want to run the program in LogicSim so that you guys can actually see what happens inside a processor when an instruction executes. Okay, so that's kind of what we want to do. So the next thing you need to do is to go to RAM file, okay? And once again, don't worry, you don't need to write down the instructions. Everything that I'm talking about right now, they are inside the lab instructions already. Okay, so you don't have to write down a single thing. Once you see me doing it once and everything is being recorded at this point, you can always kind of go back and watch it again if you need to. So we go to RAM file, and you want to make sure that A1, the cell A1, says, V2.0 and then the space and then raw. Because if the program has any type of error, you won't see this here, okay? So if you do not see V2.0 raw, that means the program needs to be fixed first, okay? Now, since we are seeing this, that means we can now, quote unquote, download the program, okay? So to download the program onto your PC, you go to File. Now, you have to do this when you are in the RAM file tab, okay? Doing this in other tabs is not going to do you any good. So you have to download the content of the program in the RAM file tab. And then you go to File, you go to Download, and then you go to one of the last two entries. I don't care which one, they both work. I usually just use CSV or comma separated value, but you can, if you want to use TSV, that's fine too, okay? That will also work. So I specify that, and it prompts me and say, what do you want to do with this? We want to save the file. In other words, do not open this, okay? Opening this is not going to help you. You want to save it. Now, this is also why you want to configure your browser not to automatically open a file when it thinks, hey, I can recognize your CSV extension. I know what to do with it. Okay, you don't want the browser to open it. You want it to save to a location. And where you want to save this file, okay, for convenience purposes, you might want to save it to exactly where you have put all the circ files, which is also handy if you put the LogicSim310 jar file into the same folder. I know it is bad from the perspective of organization, but from the perspective of simplifying the command line specification, that is advantageous when everything is in the same folder. So I'm just going to put it into this folder here, and I'll call this test.csv. Press the enter key, and now the file is saved. So now I'm going to go back to the command line, okay? And, oh, okay, I take it back. I don't need to go back to the command line. I need to go back to LogicSim. Oh, I just went one step too far. There's LogicSim. And I want to close the other window first. So let me close the hex editor for RAM first. And now I can go to the RAM component, right click on it, and then click load image. Now this step is kind of important because you don't want to do this to the ROM. Okay, make sure you're only doing this to RAM. So load image, and then we want to go to the temp folder, and I believe I saved it as test.csv. Now obviously you can use the GUI to navigate to the file and then double click it, but since I remember the full path and name of the file, I can just type it. Press open. And now you can see the content of the RAM has changed a little bit, not a whole lot, because 00 turns out to be the opcode of no op, and the opcode for halt is 01. So now I have a program that is corresponding to the instructions that I have specified in the assembler. Okay, so this is corresponding to the source file inside the assembler. And now I'm ready to run the program. So to run this program, the logic sim is already in emulation mode, simulation mode. But what we want to do in simulate is to clock it automatically. So you got a few options here. If you have a lot of patience, you can always just type Control-T many times to run the program. Or you can go to tick frequency, change tick frequency to the highest value, which is 4.1 kilohertz. And then you want to enable ticks, okay, which is Control-K. And once you do that, the program will run as quickly as it possibly can. And at some point, the program is concluded. Now, how do you know the program is done? And you can just say, okay, we're good. You can stop now. The way you can tell is to look at the halt pin. If the halt pin is a 1, that means the program is not going to do anything constructive any further. In other words, the program is quote unquote frozen, even though it's clocking. But in terms of what it is changing, it's not changing anything anymore. So at this point, you can stop the ticking. You can go to simulate, and then go back to here and toggle ticks enabled. So you can type Control-K on the keyboard as well. So that's going to stop all the ticking. And now, I believe in the lab, it will ask you some questions about locations, the content of certain things in RAM, the content of certain locations in ROM. It will ask you about the value of certain registers. Register A, B, C, and D are displayed here in binary. Now, if you want to look at these in hexadecimal, you can always click on the register bank, right-click on it, and then click on View Reg Bank. So you can look at View Reg Bank, and this will give you the hexadecimal representation of the content in each of these registers. All right, so I think that is all you need to know to get the lab done. Okay, so the lab is really just to get you to get familiarized with the tool, how to run the processor in Logic Sim, how to use the assembler, what to download, how to put content into RAM, that sort of thing. And I would suggest that you do it, like as soon as possible, okay? Because if you run into any questions, you can then ask me tonight. All right. So do we have any questions about this short demonstration of how to use the toolchain? Okay, looks like we don't have any questions. All right, so I'm gonna keep LogicSim up just in case we have any questions. And right now we're gonna go back to the module, and I will let you guys know what is the role-taking word for tonight. So we do have role-taking tonight, and the word is text toy processor. No, don't spell it out. It's just TTP. Let me type it in the text channel. Okay, so role-taking. I guess this is an abbreviation. Abbreviation is TTP. Yeah, I know. In the quiz, I mistakenly called it an acronym, but it is not. It is an abbreviation. It's TTP, which stands for Text Toy Processor. Yes, it is case sensitive. There you go. Okay, thank you, Aiden, for confirming. All right. So Now we have a few more things to go over so that we fully understand all the components. So the first thing we do is we continue with the D flip-flop thing that we started the other day. And I believe that we concluded last time on Tuesday with edge-sensitive D flip-flop. Initialism. Okay. There we go. All right, so I think last time we talked about edge-sensitive D flip-flop and also just regular D flip-flop, which is by default level sensitive. So today we're going to start with section 6. So section 6 talks about a clocked and gated D flip-flop. And this time I don't even bother to show you the text representation because it's a little bit too tedious. Okay, it really is too tedious. And if you make your own SR latch, you can actually make this circuit yourself and play with it. Okay, and this is an interesting circuitry because as you can see, we have the data pin. The data pin is an input. It is what we want the D flip-flop to remember. Okay, this is the bit that we want to remember. We have EN, which is enable. Enable basically is level sensitive. If EN is a 0, then the D flip-flop will just ignore everything else. It will ignore the clock. It will ignore the data. It will simply say, nah, I'm not going to do a single thing. And then we have clock. Okay, the clock pin is controlling the timing. Okay, given that EN is a 1, then the D flip-flop will update only when we see a transition of the clock going from 0 to 1. So at that exact moment, when it goes from 0 to 1, then whatever we see at the data pin will then become the output or the remembered state of the D flip-flop. So are we good so far? In terms of understanding, a regular D flip-flop which has an enable pin, an edge-sensitive D flip-flop which has a clock instead of an EN, and now we have a clocked and gated D flip-flop. Okay, and I believe last time I also kind of explained why we have EN and then we have clock at the same time. One way to look at this, I'll give you another analogy, and I have been told by several people, not only my students, that sometimes my analogy is, I'm thinking of the adjective. Sometimes it is catchy to the point where people only remember the analogy, but they cannot remember what it is for. Okay, so I hope this is not one of those cases. So you can kind of imagine each clocked and gated D flip-flop is an instrument in an orchestra. Okay, the EN is basically allowing the conductor to point to a particular instrument and say, yes, I'm pointing to you. It is time for you to start playing. Okay, and then the clock line is more like the beat. The conductor is trying to synchronize the entire orchestra. So in the processor, the clock is shared by all components because it is providing timing. Okay, so it just goes tick tock, tick tock, tick tock, tick tock, right? But the EN is distributed, so so that the conductor, okay, has a way to say, hey, I'm talking to you. You go ahead and update. The rest of you just ignore what I am presenting on the data pin. So this way, the conductor or the main controller of the processor can now specify, I only want you to update at this time. And the rest of you can just ignore whatever is on the data pin. So this way, we can share the data pins across multiple components and still have the whole thing to work in a coordinated way. Okay. we will get to see this a little bit better. Okay, we'll get to understand what I just said when we look at the processor and how it works. So section 7 adds a little bit more, and this time we're adding a reset pin over here. So if you think about this reset pin, okay, all by itself, okay, when the reset pin is a 1, it's not doing anything useful. Okay, let's take a look here. This portion of the D flip-flop is the same as this portion of the D flip-flop. There's no change here. So the only change is from the output of not Q, and also from the output of Q, we have some changes. Okay, so we are basically inserting this particular component here, and also this component here. This is an OR gate. This is an AND gate. This is the reset pin. So when the reset pin is a 1, okay, this little bubble here is a negation. So the 1 becomes a 0. So this becomes blah blah or 0. Well, 0 is the identity of disjunction or OR. So that means when the reset pin is a 1, it is as if O1, which is an OR gate, is not here. Let's check out the AND gate A3 over here. When the reset pin is a 1, that means we are saying blah 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 and 1. But we know that 1 or true is the identity of conjunction. So that means when the reset pin is a 1, it is also as if A3 does not exist, because whatever is the other input would just go out as if the AND gate is not here. What if the reset pin is a 0? Now it is different, because if the reset pin is a 0, then A3 would output a 0, and so that means the R pin here will experience a 0. When the R pin of an SR latch is a 0, it's going to change the output to a 0. So that means this is a way for us to initialize the state of a D flip-flop. If we have the reset pin being a 0, we are telling the D flip-flop to reset to a value of 0. So are we good so far in terms of this last detail? We're just adding a mechanism so that we can initialize the content of a D flip-flop. Because otherwise, when you power up a computer, the D flip-flops can be in any state, and that may not be what you want. So this gives us a mechanism of resetting every single D flip-flop to 0, so that we have a known start state to begin with. All right, Aiden is asking, why don't we just reuse the data pin instead of having a reset pin? Because we want to reset every or most of the D flip-flops to 0 of the entire processor architecture. So if we present a 0 in the data pin, and then we have to exercise the EN to ask each one to update itself, and then we also need a rising edge clock in order to update the D flip-flop. So that is way more complicated. The control logic to initialize each D flip-flop back to 0 using the data pin is going to be problematic. And you still need to reset that mechanism itself, right? Because you need to start a mechanism and basically say, okay, we really are starting from the beginning. So in the processor, typically they have a global reset pin or reset line or reset node that goes to every single component that should be resettable to 0, so that the state of all the major components can be reset to 0 at the same time when your processor starts up. Yep. All right, so section 8. So we look at section 8 and we say, if we turn the one in section 7 into its own chip, okay, so just kind of imagine that we are drawing a rectangle right here, okay, so we have a rectangle that encapsulates the detail of a resettable edge sensitive and level sensitive D flip-flop, and make it look like this. So this is, if you look at this diagram, okay, let me just kind of zoom in here. you will see that a lot of pins or a lot of wires are shared. This clock line here, it is shared. Okay, it's shared by each of the D flip-flops. When you look at the EN pin, the enable pin, they're also shared. Okay, you can see the EN pin is going into every single one of the D flip-flops. The ones that are not shared, or the reset pin too. Okay, by the way, the reset pin is the same way. It is shared by every single one of these D flip-flops. So what is not shared? Well, what is not shared is the data pin, because we have an 8-bit data pin here going through a splitter to split into bit 0 to bit 7. Bit 0 only goes to one D flip-flop. Bit 1 only goes to one D flip-flop, and so on. So we have one D flip-flop per bit coming in from the input data pin. When we look at the output of each D flip-flop, the Q pin, they go into a merger, and then they go to a multi-bit output pin. So we have a bit coming in, we have a bit going out, we have a single clock to control the timing to update all the bits at the same time. We have one single EN to enable the update of every single bit. And we also have one single reset line, so that if we want to reset the content of all the bits to 0, we just have one input pin to change to reset everything. So are we doing okay so far understanding this particular picture? This entire module, starting with the discussion of SR latch, is really trying to get to this point here. And this thing here, okay, so once again, imagine that you have a rectangular box, okay? So the rectangular box is really just, it's just defining the boundary of this entire circuit. That rectangular box is now known as a register. Okay, so a register is really just a fancy, I shouldn't say fancy, but it's a shorter name, otherwise known as a resettable, edge sensitive, and level sensitive D flip-flop, multi-bit D flip-flop. And that's basically what a register is. So are we okay at this point, or do we need more time to kind of look into this? Okay, not seeing any questions. So without any further questions, if I go back to the module, you will see that I have already outlined things that we need to understand. So we are now done with D flip-flop and registers. So the register is the other basic memory device. The next thing we need to do is to look into ROM. We looked into RAM, and then we look at the multiplexer and the demultiplexer. Now, I do not have my own notes on these particular items because there's help inside LogicSim. So let's go back to the GUI of LogicSim, and this time we just want to focus on the help. So if you click on help and you go to library reference, you can now look up the components that we want to look up. Let's start with something simple. Let's start with ROM, okay? So ROM belongs to a kind of memory. So you have to click on memory library. So click on that. Oh, I'm not sure whether you guys can see it or not. There we go. There we go. So you have to click on library reference. And then in here, you go to memory library. And then within there, you go to ROM. So here is the description of ROM. And this is built into LogicSim. You don't have to install anything. Once you have installed LogicSim, it's already there. So you can read the behavior. And there's really not much to say about the behavior. It has got an address port that will allow you to specify which location we want to access. And then the data port will basically reflect the content at the addressed location. Now, we do have one extra pin here called SEL, S-E-L, which is the abbreviation of select. So select is, I'm not quite sure whether I should use abbreviation or truncation, okay? But SEL stands for select. So when select is a 0, then the ROM is going to say, nobody's talking to me, and I will just leave the data port not driving anything. It's not going to, it won't present the content of anything inside the ROM. When SEL is a 1, then the ROM would go like, oh, okay, I'm supposed to talk. Which location do you want? And that's controlled by the address port. And then once we know which location we want to output, then the content at that location will then be presented at the D port. D stands for data, A stands for address, SEL stands for select. That is the overall behavior of ROM. Now we can look into RAM. Okay, so when you look into RAM, there are a few versions. Okay, so a few different ways to look at RAM. This is the typical way, which is the way that we use RAM in this particular class. So it has a lot more ports. So let's go ahead and just kind of quickly go over the different ports or pins. Once again, we have the A port, which is specifying the address. So the A port basically allows something outside of the RAM to specify an address. And whatever address is specified, the data is now linked to the D port. Now, I said linked and not being outputted to D port because it can be one or the other direction. Once again, we have a SEL. So if SEL is 0 to a RAM component, once again, the RAM component will simply ignore everything if SEL is 0, because the RAM is saying, hey, nobody's talking to me, so I'm not going to listen to A, I won't do a single thing to D, I'll just ignore everything, okay? When SEL is a 1, then the RAM chip is going to say, hey, I'm being addressed, so I better pay attention. There are several things it has to pay attention to, depending on which direction is the operation. So the direction of the operation is determined by LD, which stands for load. Okay, so when LD is a 1, we are reading from RAM. If LD is a 0, we are writing to RAM. From the perspective of RAM itself, LD means we are outputting something to the data port. And if LD is 0, it means we are inputting something from the data port. And that is seen from the perspective of the RAM itself. If you are outputting something, in other words, when LD is a 1, then the clock pin is ignored, because in that case, RAM becomes basically kind of like a ROM. So let me say that one more time. When SEL is a 1 and LD is also a 1, then the RAM component acts more or less like a ROM component. All it cares is, tell me where I need to go. The address port will do that. And I am going to output the content of the address location to the D port, which is the same behavior as a ROM. Now the next question is, what if cell is a 1 and LD is a 0? So now we are trying to update the content of RAM. So in that case, what's going to happen is the address port will still specify which location in the RAM is going to be updated. And whatever content, whatever the value is, okay, whatever the new value we want to override that location is presented onto the D port by something external to the RAM. Okay, and the clock pin is now useful because the actual update of that location depends on the rising edge of the clock. So when clock goes from 0 to 1, when SEL is a 1 and LD is a 0, then whatever location specified by the address port will then be updated based on what we see at the data port. Do we have any questions about the behavior of RAM, just kind of based on my verbal description? All right, so we got some questions coming. All right. When LD is a 1, it is okay. So we have to be careful because reading and writing has a perspective component to it. When LD is a 1, something is reading RAM. So from the perspective of RAM itself, it is writing the content of a location out to the D port. When LD is a 0, then the content addressed is going to be updated. So it will take whatever is presented at the D port and then use that to update the content that is addressed by the A port. If you're looking from the perspective of the processor, then LD is a read operation, and LD equals 1 is a read operation, LD equals 0 is a write operation. It is determined by something outside the RAM, so we don't need to know because we are controlling it. Okay, from the perspective of RAM, RAM load is going to specify to the wire. Okay, how about this? Excuse me. I'm typing on the text channel here. So when LD equals 1, then we are basically saying RAM, whatever is specified by the A port. Okay, I'm still typing, so you're not seeing anything just yet. Okay, I press the Enter key. Now we see it. When LD equals to 0, then we have the exact opposite, which is RAM A, bracket A, equals D. So when LD is a 1, then the D port of the RAM is an output and it reflects the content at the location specified by A. When LD is a 0, then whatever is addressed by A in RAM is updated to whatever is specified at the D port. Is that okay? Does everybody understand that notation? That's, by the way, a C notation. The square bracket really means array addressing. All right. All right, cool. All right. So if you want to play with RAM and ROM, you can just build a tiny little circuit to kind of exercise the various pins. This is a good starting point, by the way. Okay, this is a good starting point because you can now control the clock, you can control the address, control the store. So this store is from the perspective of the RAM itself. When store is a 1, that means we are updating the content of RAM. When store is a 0, that means we are not storing, but we are reading the content of RAM. And this is called a buffer. Okay, so this little thing here, it is not a negation, it is called a buffer. It's not a negation because we don't see a bubble here. It is acting like a clutch. When this pin here, okay, where I'm pointing to, so when that pin is a 1, that means the buffer is enabled. When a buffer is enabled, it means whatever it sees from the input is reflected at the output. Now, at this point, it is a dark green, which means, that is a 0. When it is a 0, then it is disengaged. So it is not driving the output at all. The output, it's basically just not doing a single thing about the output when the control pin is a 0. Now, if you want to read up on what a buffer does, you can go to, I think it is classified as a gate. So you can go to the gates library, which has nothing to do with Bill. And then you click on buffer. And this will tell you, what a buffer does, okay? So a buffer, basically, it is simply a pass-through depending on the control gate. So the one that we are looking at is a controlled buffer. So when we have a controlled buffer, we have a third pin. And let me see where it talks about the controlled buffer. It does not. So I wonder where it is putting a controlled buffer. Maybe under wiring. Hmm. Yeah, the one that we're looking at is called a controlled buffer. And I'm just reading the documentation here because this is just a regular buffer where it just mirrors whatever is the input to the output. And hmm, it actually does not explain what is a controlled buffer. Okay, let me just check a few other things. Huh, that is weird. It does not explain what is a controlled buffer. Oh, there we go. Okay, my bad, my bad. Okay, so this is a control buffer. Yep, okay, Alex, you're right. So this is a control buffer. It explains what each pin or what each port is doing. The west edge is the input. The east edge is the output. The south edge is the control. Okay, and it basically, if it's a 1, then the output mirrors the input. If it is a 0, it doesn't drive the output. Okay, and then Darwood is typing. I'm gonna wait a little bit. Okay. All right. So I have explained 2 out of the 3 things that I have put here. One is ROM, one is RAM, and I have not yet explained what is a multiplexer and its counterpart called a demultiplexer. So these 2 I am going to talk about on next Tuesday, but you don't have to wait, okay? Just because I'm going to talk about it next Tuesday doesn't mean that you cannot look ahead, okay? So you can certainly look ahead and go to Plexer's library, okay? Go to the Plexers and then click on multiplexer, which is a MUX, M-U-X, and click on demultiplexer, which is D-E-M-U-X. And you can just read ahead of me, because if you do read ahead of me, it's going to be quite beneficial, because then by the time I talk about it, you will have some idea of what it is. Now, as you're reading about a multiplexer and a demultiplexer, over the weekend, you might find the description here to be a little bit dry, a little bit abstract, and just not a whole lot of fun to do it. That is perfectly normal. Okay, so what I want you to do is to look up something that is potentially a little bit more fun. Okay, Thomas the Tank Engine. Okay, so we're going to use railroad, a little bit as an analogy of what is inside the processor. Okay, and the specific thing about Thomas the Tank Engine that is relating to a multiplexer and a demultiplexer are the railroad switches. So look up railroad switch. Okay, switches. And we'll go take a look at one of these switches. I used to have a pretty good set of Thomas the Tank Engine stuff. This is a good picture right there. Okay. And depending on whether the train is entering the switch or getting out of the switch, it is either a multiplexer or a demultiplexer. So now what happened to the picture that I saw earlier? Okay, because I just want this picture. This is exactly what I want. So I can just point to it. You can see how this train is coming into the junction. This is, okay, and I'm really bad with names, so I have to look it up too. So a demultiplexer has one input and multiple output. So that means this picture is representing a multiplexer. A multiplexer has multiple input, but only one single output. So this picture is telling us that we are looking at a multiplexer. So a demultiplexer is it looks exactly the same, except the train is on one of the switched tracks going out of the junction. That makes it a demultiplexer. Okay, so do we have? So that's kind of the intuitive way of looking at the switch. And then the other thing that is even more fun to look at is this one over here. This is a controlled switch. In other words, when we look at the other one, when we look at this one here, it's okay when we are merging in, when it's acting as a multiplexer because only one track has a train. But if you think about this, if there are two trains coming in, from these two different tracks, if we have no controller, okay, then they're going to collide right at the switch, okay? So a multiplexer has the capability of stopping at least one of the trains and only let one track to go through the merging. And the control, which is illustrated by this picture over here, so this one has one single input. Okay, if I want to look at it as a multiplexer, then it has two inputs, okay, 1, 2, and only has one single output over here. But the switch, the actual control of which side, which input is going to be the output, is only one single bit, because we can now label this input to be input 0 and this input to be input 1. Then using one single bit, we can now specify which one of the input connects to the output. That is basically a multiplexer. If you want to look at this as a demultiplexer, you just have to reverse the direction. We have one single input, and then we have two outputs. One output is labeled 0, one output is labeled 1. So the control mechanism is either 1 or 0. If the control mechanism specifies a 0, then the track is in this particular configuration where the input connects to output 0. If the control mechanism specifies a 1, then we have the input connected to the output 1. Then the train will come in and it will exit at output 1, or the track 1 of the output. That is really basically what a multiplexer and a demultiplexer is. Now, in the physical sense, a railroad switch is bidirectional. Okay, but in electronics, very few things are actually bidirectional. And that's why we have multiplexer, which is multiple input, one output, and then demultiplexer is one input and multiple output. And that's basically what the multiplexer and demultiplexers are. So I hope the pictures is going to help you a little bit, because when you read the actual description here, it's a little bit dry and a little bit boring. All right, so I think we're done for today's lecture. So you got a lab to do, okay, which is an exposure to the tools that you'll be using for the rest of this semester. Really, literally, we'll be using that for the rest of the semester. So that's your lab. We have road taking, where the word of the day is TTP, all uppercase. And I want you to read ahead of me as well. Okay, so go to the LogicSim documentation and read about multiplexer and demultiplexer. Okay, so those are the things that I would like you guys to do next day and also over the weekend. Do we have any questions? Oh, the lab code. Yes, I almost forgot about the lab code. And obviously, I cannot remember the lab code either. So we just have to look it up. All right, so the lab is this one. I believe it is Johnny, but I could be wrong. Let me check. Yep, it is Johnny, in honor of von Neumann. All right. Did we have road taking on October 8th? I do not remember. Yes, we did. Okay, so we did have a road taking activity on October 8th. There we go. All right, cool. So if we don't have any further questions for the entire class, I will disconnect from the voice channel, and you guys have a nice weekend, and we'll kind of study at the same time. And I'll be busy actually grading. So, I expect to have everything graded by next Tuesday. I was trying to write a script to help me grade, and then I eventually found that it's not possible, for the questions that I did ask. So I'm going to grade it manually. Just have to bite the bullet. Yep, you too. All right. Cool. Yep, probably, because I remember talking about it too. Alrighty. I am going to stop the screen share and also the voice channel, but I will stay online